So this is the third lecture. We're back to equivalence problems or applications of them today, with this time with omega functions. So this reminder from the first lecture, we solved the equivalence problem for the affine group on the line, and it was preserving a function. It had to be a non-degenerate function. A constant wouldn't work. We used it as a coordinate, but there were no other conditions on it until we got to the application, which was extreme value distributions, at which point it became a distribution. But it's just a function. So if that function is an omega function, we also know what the solution is. It doesn't change. So the stability condition for powers, taking powers of the invariant function, whatever it is, was that the product of two invariants was a constant. I was the log of f. J was the second derivative of I with respect to x divided by the first derivative squared. So in the case of the extreme value distributions, there were no restrictions on the constant. And that led to the three types of EVT distributions. So it's worth emphasizing that the condition that Ij is a constant is actually a one-parameter family of second-order differential equations. You can solve those equations to find the normal forms. And that was one of the exercises from the first lecture. So the same thing happens here. Except this time, we're going to look at powers of omega functions. Right? We want to know when is the case that they're stable. After you raise omega to a power lambda, the original omega function by doing an affine change of variables. So they're in the same affine equivalence class. And the solution can't change. It's still Ij equals constant. But this time, because we're looking at a different class of objects, there is a constraint on the constants. Not all possible constants can arise. Well, for one thing, I is the log of the omega function. We know that at the mean, the omega function is 1. So we know that I is 0 at the mean. So if I were going to be constant, it would have to be the constant 0. Now, you might still have some room to escape here because j could still be constant if j were singular and approaching the limit mu at the right rate. You could still get a constant for the product, right, through L'Hopital's rule. But that's not possible either. And the reason is the description of the omega function that Anna introduced last time. We know it can be written as 1 plus the difference between x and the mean of the distribution f over the I2 of f, the integral from x to infinity of 1 minus f of x. Now, it's an exercise to check that the value of j of mu is actually equal to 1 minus 2. That's the value of f of mu. And you can do that by using this representation of omega. That's the easiest way to do almost all of these properties, is to use that equation. So the only possible constant is 0. And of course, 0 is possible. Ixx, comma xx is 0. That's not hard to imagine. But notice that if j is going to be constant, it has to be the same constant everywhere. 0 is the only choice. And that's telling us that the distribution f is symmetric. Right? Its value at the mean is 1/2. So if we integrate that differential equation, we've got a one-parameter family, but 0 is the only parameter, so it's really one second-order differential equation. A and B are the constants of integration. And the simple normal form is just e to the x. That's the standard form, if you like. And that will have a derivative of omega at the mean. The mean is 0. The derivative of omega at the mean is 1. So the ohm for this one is 1. So this is the standard in the same way that people use the mean 0, standard deviation 1 as the standard normal distribution. This is the standard CSS distribution. That's the cumulative form of it. And it's a remarkable distribution. I mean, it's exceptional. The omega function that produces it is the only attractor under powers of omega. Right? And this distribution is also an attractor. It has to be. Right? Through the inverse formula, anything that's getting close to the omega function and it's attracting all sorts of things, e to the x, is going to have correspond to a distribution f that's getting close to this CSS. Right? So this is an attractor. And one of the exercises from last time was to show that when this standard CSS distribution has a standard deviation that's the square root of 2/3 times pi. Now, there's no pi's in the definition of CSS. We didn't need to know what pi was in order to write down this distribution. And so, of course, we don't need to know what pi is in order to make random samples from this distribution. And if you do, you should try that. If you've got a computational facility, just generate a lot of random numbers in 0, 1, invert them to get the value of the CSS there, and then compute the standard deviation of the sample and compare it with the root of 2/3 times pi. Actually, so that would be an interesting project to see what sort of convergence you get. I did a few examples the other day with 200 or 300 points, and I was getting numbers around 3, which is a good start. I have no idea how fast the convergence of this is. It might be quite slow. However,
how will you do it?
just take a random sample, right? Compute it, the sample standard deviation, and divide it by the root of 2/3. That should be close to pi, and it will be because as you sample from this thing again and again and again, the sample statistics are going to come out to be closer and closer to the population statistics. Right? As you take larger and larger samples, you're going to hone in on the population statistics. Now, the reason for that, we thought, well, this is a very interesting distribution, and nobody seems to have ever noticed it before. In fact, it's not at all clear how you would ever find this distribution without the intervention of omega functions. It's absolutely natural from omega function point of view. It's embedded in omega functions by the geometry exactly the same way as the extreme value distributions are by the geometry, and exactly the same way as the stable, Levy stable distributions are, some work in progress, by the geometry affine transformations induce on characteristic functions. Now, we actually found this originally in some work with my brother Brad on the inverse problem for omega functions, way back when we still didn't know the easy way to do most of the things. And in fact, I think the inversion formula we had was even more complicated than the one we eventually got. But anyway, that's where this is a Cascon Shadwick distribution, or a Cascon Shadwickian or something. Anyway, that it's I'll have some animations that I'll go through at the end of the lecture that show the incredible rapidity with which things converge to this distribution when you compute powers of their omega function and then back out the distribution for the power. It's absolutely remarkable how fast it is. I mean, this probably shouldn't be. It's definitely analogous to the rate at which generalized Pareto distributions converge to their EVT limits. The geometry is encoding these things in some kind of, it must be close to optimal way. So there's a picture of, of this, the standard one, the probability density function. I'll let you work out the formula for that. The standard one with mean 0, ohmic equal to 1, that's in green. And the normal distribution, again, a result of the exercise was that the ratio of the standard deviation to the ohm for a normal distribution is root 2 pi. So if we pick the sigma to be root 2 pi, that corresponds to an ohm of 1 for the normal. And you can see from the picture that the green distribution, the CSS, is slightly fatter tailed than the normal distribution. They're both thin-tailed in the sense of extreme value theory. They're both in the domain of attraction of the Gumball distribution. But there's slightly fatter tails than normal. And who knows how many places where one assumes normality, you might actually be observing CSS-ishness. In fact, it's only recently that we started looking at the geometry, the affine geometry for characteristic functions. And it was a relief to find that the normal distribution was there as an exceptional distribution. It was for a long time, we didn't have any reason, geometric reason, for the normal to exist, right? Which is not a very satisfactory state of affairs, and fortunately, it's now been corrected. So this is a very powerful attractor. Through the inverse function, you get a distribution corresponding to the lambdath power of the CSS, or the lambdath power of any omega function. That converges, not always, that converges when it does very quickly to the CSS distribution. Now, an example I'll show next time, due to Richard von Mises, is a real analytic distribution that has wiggles as it goes off to infinity that prevent that distribution from being in the domain of attraction of any EVT attractor. And that one is very interesting because it's awkward to compute. It's back out the inverses, back out the distribution corresponding to its powers, because the inverse an inverse formula requires the mean to be known explicitly, and it's one of these numbers that you it seems that it might have been studied or might not in this case, but it has no closed form expression. So I'm come back to that a bit later today. It turns out that there's a workaround for that through a different type of stability that we'll come to later. And the Gumball distribution is another example of that. The Gumball distribution's mean doesn't have any known closed form expression. It's got a name. It's the Euler number, apparently. And it's a remarkable thing. Some of the combinatorial types might know something about that. It's been shown that it's not known whether it's rational or not. However, it's been shown that if it's rational, the numerator and denominator have to be staggeringly large integers. I mean, 10 to the 20, something like that, maybe even more. So it's highly probable that it's an irrational number, but nobody knows. And unfortunately, that means it's difficult, I mean, it's impossible to exactly compute the distributions corresponding to powers of its omega function. They all exist because its mean is finite, so its omega function is well defined. The powers are all fine, but it's not possible to use that form without an exact. Well, it's possible. You can approximate things quite well by using machine precision value of the mean.
Sorry, I'm getting confused. Can you summarize this?
I'll come back to it. Yeah, this is the magic formula for the inverse, and it has the mean right here. So if we take powers of omega, the mean is the place where omega equals 1, so it's also the place where omega to any power is equal to 1. The trouble is that doesn't allow us to calculate it. Okay. Unless we can through some clever symbolic manipulation or otherwise get an expression for the mean, we can't really use this formula. Now, it turns out that there's a cheat that seems to work reasonably well. It seems to work quite well so far. So we'll see how that just started applying that. So the induced distributions are the things we're really interested in. I mean, the omega functions are important, but we're interested in the distributions. That's the thing we use to compute probabilities and so on. And that's the format in which it's most convenient to watch the convergence. But there has to be a convergence. If omega lambda's converging to the CSS omega, which is e to the x, then f lambda has to be converging through this formula to the CSS distribution. So this is the first omega function I ever calculated, and I don't even think was using Maple at the time. It was just calculated by hand was for the normal distribution. And that was the place where we realized that something important was going on, because we could see that the tangent at the mean was generating some multiple of the standard deviation for the normal distribution. So that was in the prehistory of these things. But I think the next example that I did was a special case, the mean zero case of the Bernoulli distribution. So just a simple coin toss. 1/2 of the time you're on -1, 1/2 of the time you're on +1. And I mean, think of that distribution as 1/2 times the delta function at x minus 1 plus 1/2 times the delta function at 1. Or a discrete distribution with two data points. Well, with one data point, you don't have an omega function. But with two, you do already. So the most fundamental, simple thing is the omega function for the coin toss, which is the mu equals 0 case of this. And that generalizes easily to the Bernoulli distribution, where here we're parameterizing Bernoulli by its mean rather than possibly more common by parameterizing by the probability of it being -1 and 1 minus that is probability of being 1 and so on. But it's easy to see it's the same thing. And in fact, obviously there should be a lambda here as well. So we take that simple case and raise it to the power lambda. Now, this was one of the exercises from last time, so it's simple to check that's what's going on. And you can, I mean, it's very helpful to have a symbolic manipulator to do these two arbitrary powers. But for example, it's also very easy to see that if you take mu equals 0 and lambda equals 2, you've got the omega function for the uniform distribution on the interval from -1 to 1. Now this, the one parameter family that comes out of this has many remarkable properties. It's quite an extraordinary object. So first of all, we can just differentiate to get the value of the ohm that corresponds to these to the version with the parameter lambda. We just have to differentiate and set r equal to mu. Okay. And this shows something that's a common feature here. That as the power increases, the ohm is going to tend to 0. You're going to get closer and closer to a delta function spike as the power increases. But it's not a standard, if you like, standard delta function. It's not a Gaussian delta function. How do you know? Well, you compute the character. You compute the ratio of the standard deviation to the ohm. If that's not approaching √2 pi, you're not approaching a Gaussian delta function. And in fact, you're not. What this approaches, because of the attractor of the CSS, is it has to approach this has to approach the CSS density. Has the wrong character for this to be Gaussian. So this distribution is useful. This family of distributions is useful in potentially many different ways. But one of the things that we think is important about it is that the way it interacts with data samples. When you have a sample of data, you have a sample that's on a finite interval. X min to X max, there's nothing infinite there. So, and every finite interval can be mapped to -1, 1 by a unique choice of the two parameters in an affine transformation. So you can always do an affine transformation which doesn't change probabilities. You can map your data onto this standard interval. But it turns out you can do that in a way that preserves the mean and the ohm. So you're fitting through this family of distributions in a way that preserves the mean and the ohm. And what it boils down to show that is that if we have a distribution on -1, 1, then it's got a mean somewhere between -1 and 1. It's got an ohm. And if it's going to fit in this family, the mean and the ohm have to be, and the lambda have to be related by this identity. So we need to know that lambda is greater than or equal to 1. So these things are not defined. You can't take a square root of the coin toss distribution. Power 1 is what you can do, and you can do every power above that. You can do the power pi, you can do the power, anything you want that's bigger than 1, but you can't be smaller than 1. Now you can be exactly equal to 1, which is what happens with the Bernoulli distribution, right, as you can check. Well, in fact, that's sort of where we started. When lambda is equal to 1, this is the Bernoulli distribution. Okay. So we have to show that no matter what mu and ohm and the ohm are, this relationship will always allow us to have a lambda, which it'll give us a unique value of lambda, of course, and that value would be greater than or equal to 1. So the proof of that is basically the generalization of the pictures you saw for the proof of the Markov inequality and the identities about the ohm last time, to the case where those diagrams were the case where the distribution was non-negative. The random variables were non-negative. It made it simpler. Now we've got to worry about the mean anywhere in the interval from -1 to 1. But because omega is the mean, the integral, the area under f over the interval from -1 to mu, then it has a largest possible value when it's just mu plus 1 times h. So the case where normally we think about the distribution like this, but in fact, it can be like this. This is mu. In the case of a Bernoulli distribution, it will be. Okay. And then the rest of it up here, like this. And in fact, it is in the case of Bernoulli distribution. But so this area could be as big as 1 plus mu times h, right, where h is the height, at which we hit the mean. Okay. So let's assume that that's the worst case. So let's start there, assume that it is. But these things have to balance at the mean. So the ohm can't be bigger than this rectangle either. So this gives us a bound. The ohm must be less than or equal to this product. It can't be, it could be as big as this, but it can't be bigger than this. Okay? So that gives us the inequality. And that tells us that twice h is less than or equal to 1 minus mu. So you should go through this argument. It's really just this picture. From those two equations, the assumption that the ohm is taking up this whole space, and the next one, we see that we can factor the 1 plus mu from the numerator and denominator, and we get 1 minus mu over 2h, which must be greater than or equal to 1. So that means we can always fit anything with one of this family of deformed, anything on -1, 1 is uniquely fit by the lambda element of this deformation on -1, 1, the corresponding distribution to that. And so anytime we have an empirical distribution, we can transform it uniquely to -1, 1 by sending x min to -1, x max to 1. That'll determine the affine transformation. And the pullback distribution has to have the same sample, mean and ohm. And that's what was behind the idea of the shape score that we introduced last time, which comes from looking at the logarithm of an omega function. You have an omega function on AB. Then the omega function goes to 0 at A, infinity at B. You take its logarithm, you get something that's a little more interesting looking. And it's 0 exactly where the mean is. So looking at the difference between this area and this area gives you a good picture of how asymmetric the distribution is. And that's what we're doing here. To do that, of course, the A and B don't have to be finite, but it's simpler when they are. And then the formula says, well, that's really just lambda times the logarithm of this ratio of means. So you see that it's positive when the distribution is biased to the upside, negative when the distribution is biased to the downside. Oops. So that's immediate from what we've just done. But when you look at what this is made up out of, in terms of the data, it's very nice. It's easy to check, right? You see that this is affine invariant, right? It doesn't change with translations, and the numerators all scale in the same way as the denominators. It just wipes out the scale factor. Okay. So that's an affine invariant. And it's actually a very informative invariant about the data set. We saw this last time. This is just for a couple of examples. I mean, this is just data, so it's irrelevant whether the samples are the same size, whether they come from the same time or different times. It's just data. Right? So we call this the data transform. And we're currently looking at more and more applications of it.
Isn't that why it's good to transform them in the same interval? To make it relevant?
Yeah, so now this is a standard of comparison. Everything might as well be on -1, 1. So this is, remember the second equivalence problem that we addressed in the first lecture was equivalence for what Anna decided to call peak under threshold. So it's really the conditional distribution F, conditional on falling below a certain threshold in the domain of F. So we can do the same thing with an omega function. The omega function is positive everywhere. It's never 0. It tends to 0 as you get off to the left-hand end of the support. But anywhere in between, in the open interval from A to B, omega of z is not 0. And this, we simply divide the omega function by its value at z. That's going to move the mean, right? because the new omega z is going to be 1 at z. It's stationary if we use z is equal to the mean, nothing happens. But if z is not equal to the mean, then there's a new omega function. And we can invert it through the inverse formula, where this time we have to take into account the fact that the mean has changed, but we know what it is, it's z. So this is an example of how we might use the deformation of, in this mode, with an approximation of the mean. So if we can't compute the mean exactly, we get the machine precision approximation of it, and we divide the omega function by that. Right? That puts the mean exactly at our machine precision approximation, but it's going to be very close to, everything is going to be close to what it was before. So it would be, we're looking at examples to see how reliable that notion of close is, because you never really know what the topology is in these spaces. We might get some surprises. So this is the second stability condition. We want to know, when is this not changing things by more than you can undo with an affine transformation? Right? That's the stability condition. And we saw in the first lecture that stability condition, independent of what the function was, just a matter of the equivalent, we were taking the equivalence class under affine transformations. It was j equals constant. But from exercise 1, we just went by, the constant has to be between -1 and 1. Okay, that was yeah, okay. J is going to be a constant. It has to take the same value everywhere that it does at mu, and that means it's between -1 and 1, because f of mu has to be bigger than 0, and it has to be less than 1. So that's the constraint on our constant. Right. So the solutions to this problem are the omega functions that correspond to j equals constant, where the constant is in the open interval from -1 to 1. So this is the second exercise. And, again, we found these things before we looked at the equivalence problem, but the right way to find them is by looking at the equivalence problem. See, there's no question about what's going on here. It's a machine. Now, there's the parameterizations here are always annoying, but these are powers of x. If you look on the first case, that's defined on the interval from 0 to infinity. It's just powers of x rising. In the second case, powers of negative x are rising when you're taking -1 over c, right? And that's defined on the interval from -infinity to 0. Okay. So there was a point glossed over here. Equation 16 says this is what the distribution looks like in terms of omega sub z. But the question is that really a distribution? Okay. Now, the hint is a big hint. We know when we start off with an omega function that that's the inverse function. That's the inverse formula. So that inverse formula has all the information in it you need to conclude that f is increasing function that goes from 0 at A to 1 at B is increasing throughout the interval. So there's enough information in the right-hand side of that to prove that. And what we have to do now is use those properties of things on the right-hand side, adjusted for the fact that we've got omega z instead of omega, and show that they're still true. So the f is a distribution. Once you know f is a distribution, then you know omega z is an omega function because it's the omega function of that distribution by the inverse formula. So there's a bootstrap aspect to this, but that's the process. And the last thing about this particular process that I wanted to notice is that that's exactly how we go from the coin toss omega function with mu equals 0 to the general Bernoulli omega function. Because that 1 minus a over 1 plus a is exactly 1 over the value of omega at a. Okay. In the original coin toss. Okay, so it's, I mean, I don't know how many times I've used the word remarkable in this series so far, but this is, I think, really remarkable. You start with this sort of atomic elemental omega function. Right? The coin toss distribution. Using this stability, you generate the Bernoulli distribution from that one special example of it. And then you have this whole family of distributions that culminates in the CSS attractor. And it's all done, this whole thing is all stuck together by the geometry of the affine group. So the same invariants that we used to pick out the extreme value distributions, they were simply the result of integrating those one-parameter families of second-order equations. We had, in that case, the parameter could be anything from minus infinity to infinity. But the conditions, the invariants tell us what's possible. So we get exactly the same process with omega functions, the difference being that instead of a one-parameter family, we get a single point, like the Gumball distribution in the extreme value examples. And for characteristic functions, for example, the normal distribution and the Cauchy distribution both arise in exactly the same way. Talk about that later. And I want to emphasize that that's the the fact that differential invariants equal to being set equal to constants are what drives these things is, in the case we know, is just a matter of a family of second-order ordinary differential equations. So this is a very simple, well, those equations are actually quite remarkable. They all have, in the extreme value case, and I guess we haven't looked at that, but probably here too, there's a natural variational problem. The ODEs for the extreme value invariants are all Hamiltonian. They're all Euler-Lagrange equations, which of course not every second order ODE is. Right? That's another special aspect of this thing. But you would never find those without the equivalence method, without the geometry guiding you. How would you ever find those quantities? So in the next lecture, we want to go on to this theorem, which is that if you start with a distribution on AB, which is in the domain where, again, these can be infinite or finite. When it's in the domain of an extreme value distribution, then you must have the same invariant as the extreme value distribution does in the limit, right? You can't be approaching that distribution if your invariant is not approaching the invariant of the distribution. And then we want to show the converse, that if the two invariants are approaching, the distributions are approaching as well. And that's really because these are ordinary differential equations that characterize the invariant and the constant case. So in the first lecture, I also introduced the solutions to the case of distributions that had j equal constant. And there, every constant was possible. Those were all distributions on negative half lines. But what I think was left as an exercise, but it's a very simple matter to do. If you look at the mirror image of that, meaning take from the distribution G, you take G hat, which is going to have be 1 minus G at minus X on the other side of it. So it's the distribution corresponding to the mirror image probability density function, which all of these things have. Then those are the generalized Pareto distributions that mysteriously appear in the middle of every treatment of extreme value distributions. And there's a reason for that, because these things are dual. The things that are being, the j equals constant are attractors as you move off to the left. The ij equals constant are attractors as you move off to the right. And there's a duality between those domains of attraction. It tells you how to match up a j equals constant with an ij equals constant on the other side. And that, sorry, before we get to the movies, there's much more there as well, because it's very, I found very frustrating looking at the extreme value literature. I suppose it's because I'm not an analyst. So I have a certain aversion to some of these kinds of treatments. But the one very striking thing is that the move from the original work of Fisher and Tippett and some of their predecessors to Gdańko's conditions for something to be in this zone of attraction, domain of attraction of one of the extreme value distributions, is a transition where you completely lose the power, the power of n. You raise the different distribution to the power of n. That was how it all started. But the solution has nothing to do with n. Of course, that in our setup is that this invariant I times j is absolutely independent of the power lambda that we're raising things to. So the solution has nothing to do with lambda, if you like, the fact that you're raising powers. It has everything to do, and you see this in Gdańko's conditions for equivalence for being in the domain of attraction of Weibel and Fréchet distributions. It all has to do with the shape, asymptotic shape of the distribution. Okay. And that's exactly what the invariants are measuring. Okay. So that's, so we also want to look at, I mean, this is something that we did a lot of recently because of the application of Gompertz functions, which is just a constant multiple of the Gumball distribution, positive integer multiple of the Gumball distribution, to viral evolution. And that's a matter of fitting Gompertz functions, which amounts to fitting the Gumball distribution with one other parameter, to data. Now, the standard approach to these things will say, well, we can do an affine transformation on our distribution and make it fit the standard Gumball distribution. What's much more sensible to say, here's my distribution. I might have a mean of 4 and a standard deviation of 14 if it's, but it doesn't matter. Now take that, don't transform it, just tell me what Gumball distribution it's going to hit. And that's a simple nonlinear regression problem. Find the Gumball distribution that fits this tail of your data. And the experiments we did with that showed that the fit became very good remarkably early in the tail, if you think in terms of quantiles. In lots of cases, you see things converging so well that you can't see the difference between the two curves anymore. And that's not the best measure. But by the 50th percentile. So there's an indication that these things occur in nature quite strongly. And we'll look at that as well next time. But I want to look at some examples of these deformations through some animations that show how rapidly they converge to the in the case of omega functions and their induced distributions to the CSS.
Yeah, I think the biggest proof we have that the Gumball is important in nature is the basis for the behavioral virus, right?
Well, that's it. Yes, that's
we
definitely
did
an important one.
a full epidemiological model. It's a Gompertz function,
Yes,
which
yes,
is basically the Gumball distribution. And with examples from Zika, dengue, COVID-19, influenza, and it is intrinsic to the virus development, the Gumball distribution.
Right, and this natural variational problem, I think, has something to do with that. So anyway, we'll come to that next time, some more examples. So. The movies. Here's an example of convergence to the omega through the deformed omega functions to the CSS. That the green is CSS with the mean in the ohm that we've started off with, and we're adjusting things so that we don't get a delta function. We're just rescaling. Right? The red is the original probability density function. So that's a pretty, meant to look like a little omega. But that's nowhere close to a standard PDF, right? It's starting from behind in all aspects, and yet, as you take its omega function, and of course the cusp doesn't matter. This is the PDF. We integrate once to get the distribution, and then again to get the omega function. So we've got 1 degree of 2 degrees of smoothness more than this cusp thing by the time we get to the omega function. But as you deform the omega function by taking powers, you get back out the probability density function. That's the blue curve.
So the alphas are lambdas.
Sorry, I forgot about the change of notation. The power is alpha, and see, we're only going up to 4. But that's the extraordinary rate at which the thing is convergent. This is the corresponding invariance. The green is the invariant, the constant 0 invariant. Red is the initial. blue is the result of the deformation. So that's the evolution of the cumulative.
Which distribution?
This is the same picture. It's just instead of the probability density function, we're looking at the cumulative now. And here's the invariance as we go through that process. So the convergence is just lightning fast. You can see that it takes a long time for the invariant to get to zero everywhere. It gets close to zero very quickly around the mean. But the cumulative and the probability density approach the limit, the CSS, very quickly. So the invariant is the thing that takes the longest. But it's doing most of its work near the mean.
So what's the invariant one?
The blue. So that's ij, or j rather, for the omega function of this silly looking distribution. Who is the induced distribution for the powers, alphath power of its omega function.
What is this representation?
Sorry?
What this representation is? The other one.
This is the invariant. This is J.
This big J, okay.
Okay, this is the probability density function, and we have the cumulative distribution. And the third one is the invariant.
That's the cumulative.
That's the cumulative. And it's got two wiggles in it in the red because of that hump in the middle.
That's the invariance.
That's the invariant. See, it's fairly constant asymptotically, but it's the wrong constant, but it's heading down towards zero. Anyway, that's enough animation.
That's all, folks?
That's all. Oh, well, maybe, let me see if I can. Oh, yeah, this is the animation of the deformation of the three different Bernoulli distributions. The blue one has mean 0. The other two have positive and negative means. They're different. They're all approaching CSS distributions as lambda goes on. You see at the beginning, you have something very flat. At lambda equals 2, you get, for the blue one, you get a uniform distribution, so that the PDF is just horizontal. You see it's starting to slip down, and then it gets bell-shaped before long. And again, I think that this one goes up to, what, 6 or so, maybe 10, I remember. 8, okay. So we don't need very many iterations before these things just hone in on the limiting CSS. Just focuses on the.
Sorry?
This is the same family. Green is the CSS that has the same ohm as the blue as we go through. See, it's getting closer and closer. Again, we're going to 8 here. Oh, maybe this one went to 10. So initially, for the coin toss, you're effectively having two delta functions, right? One at each end. And then it's slipping down from that, and it's popping up. So the dynamics is very nice. Anyway, that's a good place to stop. And we'll come back to the proofs of the theorem next time.